This week we're going to be looking at the Manova and the Mancova. And what we find with these two is that we're going to conclude our series of statistics that are measuring group differences. This is something that we began in EDU 9615 when we began the single sample t-test and moved through the ANOVA, and now we're come through the other aspects here in 9616. And we conclude the group differences set of statistics with the Manova and the Mancova. Now, for a full review of all of those statistics, you can look at page 15, which begins section 2.2 in your textbook, and it really gives a nice summary of what you need to really get in your mind about what groups, variables that you would use as you move through this set of statistics that are working on this group differences. Now let's talk about some of the key distinguishing traits that go along for the Manova and the Mancova. For the Manova, you have two or more independent variables that are categorical. Now this is very much like the ANOVA in the things that we've been doing, but what's different along with this is the idea of you have two or more dependent variables that are quantitative. And so you see you have more independent variables than one. You have more dependent variables than one. You add one or more covariates to the Manova. So you can see how these two build on what we did with the ANOVA and the Mancova. Now, some of the advantages: both of these statistics provide the researcher an opportunity to reduce the error possibilities. As we've discussed in previous ones, you could do single tests for each of the variables that you're looking at, but in doing this, you add a lot of possibility for error. Doing the Manova and the Mancova together, you reduce those error possibilities. They also provide insights not seen when just a single variable or single variables are examined. When you bring them all together, there's a way of mathematically looking at how they interplay with one another, so you get a better picture of what might be going on, so your insights are better than if you just did a single test. Some of the disadvantages: they're difficult to compute. In fact, it's really because we have the computers and the power that we have the computers that we're doing these, because the number of mathematical iterations that are necessary. Notice that in these multivariate statistics that they're showing you some of the idea behind it, but most time they're not even showing you the formula that you would use, because they're so complicated that we do these by the use of the computer. Also, we might find combination of variables that really go together. And this is very important because as you think through what variables you're going to use, they have to make sense. Now, one of the ways that you do this is through your literature review, where you begin finding discussions of variables that might relate to one another. And then out of your literature review, you also see theoretical concepts of where these variables might come together and what set of variables play into making a possible effect on an outcome that you're looking for. Now, what do we do? What are the results that we're looking for? The researcher most often computes the Wilks lambda, and that's the Greek letter there. And if you want to type this in anytime in your reports or something in Word, you go up to the font and come down to symbol, and you will see that the symbol font are the Greek letters, and the lambda would be the capital L, and that will give you how to print that out. The same thing is with the chi. You can go to symbol and look at where the chi is. It's either going to, I believe it will be the X, and that will show you how to work that out. Now, the lambda has an obtained value of between 0 and 1. And here it's sort of a reverse idea from what we've been doing. Here, the smaller the number, the more evidence of treatment effects causing the observed difference. So that lambda, as it gets closer to 0, we see more possibility of it being statistically significant. Now, what are some of the assumptions? This goes along with the central limits theorem, that we have random sampling, and also that the samples are independent of one another. so that there's not an interrelated relationship between the samples themselves. Secondly, we need a multivariate normal distribution in each group. That's a little different than just a normal distribution, the multivariate normal distribution. So between the variables, there has to be a normal distribution. Then we have a covariance matrices for the dependent variable of each group must be equal. So again, when we look at putting these all together, the dependent variables have to have a covariance that's equal. Then the relationship of the dependent variable pairs for each cell in the data matrix must be linear. And so we have to look for that linear relationship among the dependent variables that we're looking for. Now in testing, continuing on, in testing for that normality, we would look for elliptical patterns in the scatter plots, and we would review the skewness. For homoscedasticity, we would use Box's test, and it should not be significant, and that shows us that. And then for linearity, we go back up to our bivariate scatter plots, and again, these should be elliptical. So again, we look at those three areas that we've been looking at our data all along. Now, the Manova and the Mancova can handle some violation of these, but if we can, we transform the data, and that will improve our results. Now, interpreting the results, we're going to look at the Box's test. If not significant, then we're going to use the Wilks lambda. If it's significant at the 0.001 level, we'll use Palais trace as the results of our Manova. Then in our factor interactions, we're going to look at the F ratios, which is the ANOVA, which will be computed as a part of the Manova and Mancova computations. And we'll look at the p-values with 2 or more of the independent variables to see how that interaction is going. If significance is found in the Manova, then we're going to go back to examine the ANOVA and see where that difference is occurring. It's sort of like our post hoc test for the Manova by using the ANOVA. Now the Mancova is just like the Manova in having more than two or more independent variables, 2 or more dependent variables, but what we now add is we have 1 or more covariates. And by removing the effect of these covariates, we're able to get an even clearer picture of what's going on between our main independent variables and dependent variables. And it reduces that unwanted error. And one of the other things that you can do with the Mancova, if you have groups that are intact where you weren't able to choose them from being random, you can adjust them for some of the ideas that may cause them to be less than random. And so that's one of the areas that the Mancova, it comes in that covariate can be a variable that makes these intact groups more like random. And the covariates need to have a significant relationship with the dependent variable. There has to be something about that covariate that is interacting with the dependent variables. Now the assumptions, random and independent. Now here is what's different in the wording of the assumptions. The dependent variable distribution scores are normal in the population. And here we're looking at that, how these all work together and are they normally distributed. And the same thing is true with the equal variances. The distribution scores have to have equal variances. And all the relationships must be linear. If 2 of the control variables, you look at regression planes and must be homogeneous or parallel. So you see if you've got 2 control variables, their regression planes must be homogeneous or parallel. If you've got more than that, then you're going to have to look at the box plots. The control variables must also be able to be reliably and accurately measured. So like sometimes in the past when we did Mancova, we had gender that can be very accurately measured. And it's very reliably measured. And so the covariates need to be very well measured as you work through them. In testing the Mancova assumptions, we're first going to look at the normality of the dependent variables distribution. And we're going to look at skewness, we're going to look at kurtosis, and then we look at this test that we've been seeing, the Kolmogorov-Smirnov test, and that is a part of the normalcy function that when you're computing, that will come up and you will read that. And you want that to be not significant. Then our homoscedasticity, we're going to again use Box's test. And if we're not able to use it, then we go to either Hartley's Fmax test, Cochrane's test, or Levine's test, which we've used in the past. For linearity, it's very difficult to do this because you've got all of these variates working together. So you just do a bivariate scatter plots, and you check those, and you're looking for them to be elliptical. Now, a lot of this will come more clear when we do our work through in the examples in the textbook for the Manova and the Mancova, and you'll see these three areas, normality, homoscedasticity, and linearity, how those interplay as we work through SPSS.